Spectre. Spectre was one of the first and most shocking CPU flaws ever discovered. It works by taking advantage of how modern CPUs guess what you'll do next, a feature called speculative execution. When a program runs, the CPU doesn't like to wait. It tries to predict the next instruction to save time. But when it guesses wrong, traces of what it just did can stay behind in the CPU's memory. Those traces, like tiny footprints in the sand, can reveal information from other programs. A hacker can carefully measure these traces and piece together secrets like passwords or encryption keys. What made Spectre terrifying was that it wasn't just a bug, it was a design problem in almost every CPU on the planet. Fixing it required both software updates and smarter CPU designs that hide their guesses better. Meltdown. Meltdown is like a broken lock on the CPU's door. Normally, there's a wall between the kernel, the heart of the operating system, and user applications. That wall keeps your apps from touching sensitive system data. But Meltdown lets an attacker jump over that wall and read information directly from the kernel's memory. It takes advantage of the CPU's ability to run instructions out of order for speed. The CPU accidentally lets one instruction read protected memory before realizing it shouldn't have, and then tries to cover it up. But by that time, traces are left behind that can be read using timing tricks. It's like sneaking a peek inside a safe before it's locked again. The discovery of Meltdown in 2018 forced every major tech company to redesign how their systems interact with the processor, and even though patches fixed it, they slightly slowed computers down because safety replaced speed. Foreshadow. L1 terminal fault. Foreshadow digs even deeper into the CPU's inner layers. It targets the L1 cache, a super-fast memory area that stores temporary data the CPU needs right away. Inside that cache might be information from virtual machines, other users, or even secure areas like Intel's SGX enclaves, private digital vaults meant to protect data. Foreshadow cleverly tricks the CPU into revealing what's inside the cache by exploiting speculative execution again. It's as if the CPU was dreaming about data it wasn't supposed to see, and that dream left fingerprints behind. This vulnerability was especially worrying for cloud providers, where many users share one physical CPU. Fixing it required firmware updates and stronger isolation between virtual machines, proving that even the smallest design flaws can create massive security holes. ZombieLoad. ZombieLoad is part of a group of vulnerabilities called microarchitectural data sampling, MDS. These flaws target the internal buffers inside the CPU, small holding areas used to temporarily store information as it moves between the processor and memory. Normally, these buffers are emptied quickly, but ZombieLoad found a way to read the leftover data that wasn't fully cleared out. Think of it like a restaurant where each table isn't wiped clean after customers leave. The next person could see what the previous guest ordered. This means a malicious program can spy on what another program just did, potentially reading sensitive data like browser history or encryption keys. Fixes required microcode updates that sanitize these buffers after every task, making sure no crumbs are left behind for someone to analyze. Rowhammer. Rowhammer isn't a CPU logic flaw, it's a hardware effect that happens in computer memory. But it's deeply connected to how the CPU accesses that memory. In DRAM, which stores your data as tiny electrical charges, flipping one row of bits repeatedly can cause nearby rows to accidentally flip too. That's why it's called Rowhammer. You're hammering a memory row until neighboring bits flip from 1 to 0, or vice versa. Attackers realized they could use this to change memory they weren't supposed to touch, even altering permissions or taking over parts of the system. Modern CPUs access memory so quickly that this effect can be triggered through software alone. To prevent it, memory manufacturers added features like ECC, error correcting code, and TRR, target row refresh, that automatically fix or refresh cells before they flip. But Rowhammer proved that physical effects can still become digital security risks. LVI. Load value injection. LVI, or load value injection, turns speculative execution upside down. Instead of reading secrets, it injects fake data into the CPU's guesswork. Imagine someone whispering the wrong answer into your ear while you're solving a puzzle. That's what LVI does to the CPU. It forces the CPU to use incorrect values during speculative execution, potentially making secure software perform unsafe actions. This attack is especially tricky because it can even target CPUs that have already been patched against Spectre and Meltdown. Researchers discovered that LVI could affect Intel's SGX, a feature meant to isolate sensitive information from the rest of the system. The only reliable fix was to disable certain speculative features altogether, which once again came at a cost. Slower performance, but safer computing. TLBleed. TLBleed uses the CPU's translation look-aside buffer, a cache that helps the processor quickly find where data lives in memory. It doesn't read memory directly, but instead listens to how the TLB behaves. By watching the timing of operations, attackers can guess which memory areas another program is accessing. Over time, this can reveal sensitive information, including cryptographic keys. It's a bit like eavesdropping on which drawers someone opens without seeing what's inside. Just knowing the pattern gives away secrets. The TLBleed attack was especially powerful on CPUs with simultaneous multithreading, SMT, where two programs share the same physical core. The fix was to disable SMT in some systems or to isolate threads more securely, ensuring that timing information couldn't be shared between programs. PortSmash. PortSmash targets how CPUs handle multiple instructions at the same time using different internal ports. Each port is like a lane in a racetrack. When two programs share the same CPU core, one can measure how long its own instructions take to finish. If they slow down at certain times, it means the other program is using the same port. From these small timing differences, the attacker can infer what kind of operations the other program is running, even decrypting private data. PortSmash showed that even without reading memory directly, timing alone can be dangerous. The lesson from PortSmash is simple. Shared resources can create silent channels of information, and the CPU must separate them better. Plundervolt. Plundervolt is an attack that messes with the CPU's power supply. Modern processors can adjust their voltage and frequency to save energy, a feature called dynamic voltage scaling. But researchers discovered that if you slightly lower the voltage at the right moment, the CPU can start making calculation mistakes. Those mistakes can be used to break security features like Intel's SGX. It's like flickering the lights in a safe room to make someone misread the numbers on a lock. The fix involved firmware updates that disable software voltage control in secure environments. Plundervolt reminded engineers that even physical properties like electricity can become weapons in the wrong hands. Downfall. Downfall is a newer vulnerability discovered in Intel processors that affects a special CPU instruction called gather. This instruction collects scattered pieces of data from memory quickly. The flaw allowed leftover information from one program to leak into another's. Gather operations. It's as if two people shared the same scoop to get their ice cream, and bits of one flavor stayed behind. Downfall could expose sensitive information from cloud environments or even encrypted processes. The vulnerability was serious enough that Intel released microcode updates to mitigate it, and some data centers had to temporarily disable gather optimizations to stay secure. Downfall showed that even single instructions, deep in the CPU's hardware, can carry unseen risks. Inception. Inception is a vulnerability that sounds straight out of science fiction, and it behaves like it, too. It manipulates the CPU's return predictions, creating layers of speculative operations that leak data, a dream within a dream, just like the movie. It primarily affects AMD chips and uses speculative return instructions to confuse the CPU's prediction system. The result? Data from protected memory can leak into user space through mispredicted branches. Inception proved that the more advanced and predictive CPUs become, the more ways exist to fool them into revealing secrets. AMD's fix involved microcode updates and better control over speculative predictions. Retbleed. Retbleed is another vulnerability in the Spectre family, but it takes a different path. It targets return instructions rather than branches. When a program calls and returns from functions, the CPU predicts where to go next. Retbleed poisons that prediction mechanism, causing it to speculate into areas of memory it shouldn't. This speculative journey leaves behind traces that attackers can read. Retbleed was particularly nasty because it affected even CPUs that had been patched for older Spectre flaws. Once again, software and microcode updates were needed, and the pattern was clear. Speed-oriented features, like branch prediction, needed to be rethought entirely for future CPU designs. All these vulnerabilities, from Spectre to Retbleed, teach the same lesson. The faster and smarter our computers become, the more creative their mistakes get. Every time engineers invent a new way to make processors run faster, they also create new corners for data to leak through.